A marvelous new feature has been added to the Daikin single-screw compressor. A capacity control mechanism that steplessly varies capacity between 30 and 100%. The major benefits are again simplicity and reliability. Before elaborating on this, let us first examine the main parts of the compressor. To the far left side, the compressor inlet. Moving to the right, the electrical motor, then the compressor itself, and finally, the oil separator on the far right. Besides the nameplate on the compressor, we find that instead of the flanges, a suction valve and a discharge valve can be mounted. Plus a flare connection for the low pressure and the high pressure measurement. On top, we see the body of the 12% capacity solenoid valve. Below this, two oil drain connections. Then the oil level side glass. That, by the way, includes a nice feature that assists in correctly interpreting the reading. This oil level indicator has clear vertical markings on the glass. These markings, however, are not visible when there is oil behind them. So when the marks are visible, as is the case now, there is no oil in the compressor, a situation that certainly requires attention. Back to the general view. The crankcase heater will be inserted into this bottom right position. Now, to explain this compressor, take a look at this cutaway version. At the bottom left of the oil separator, we see where the heater is inserted that is designed to maintain the oil temperature when the compressor has stopped. To allow us to operate this cutaway version, parts were added on the main shaft. Isn't it remarkable how few moving parts there are? Let us follow the flow of the refrigerant through the compressor. First, through an optional suction valve and inlet filter. The suction gases will then flow over the windings of the electrical motor, using the various channels for the required cooling, and thus also avoiding liquid refrigerant reaching the compressor section. Underneath the switch box, we see the connections of the windings and the CTP, the compressor thermal protector. We already noted that there are few moving parts. Indeed, the unique screw makes use of a direct drive, and consequently, no gearbox or other transmission is required. The screw is thus mounted on the same shaft as the rotor of the electrical motor. The capacity slide will be controlled by the stepless mechanism that we will discuss later. Note also the red part, the discharge chamber. This discharge chamber will act as muffler or sound attenuator, and, importantly, also lightens the construction. This light construction will easily absorb the expansion due to the compression heat, thus preventing the machine from seizing up. The part inserted through the discharge chamber is the connection of a possible economizer. Gate rotors are also essential parts of a single-screw compressor. The upper gate rotor is the one we can see here. The lower gate rotor is invisible now, but it is located at the same height on the other side of the screw but flipped over. This balances the forces on the screw, so that no radial force is exerted on the bearings. The compression will occur in the grooves using the fingers of the upper and lower gate rotors. This upper gate rotor is made of 8 mm engineering composite. Note the nose of the gate rotor. These horizontal ribs assure proper sealing at the bottom of the groove or compression chamber. Notice also how the composite material is loosely supported and kept into position. Here we see how the capacity control slide moves between 0 and 100%. Contrary to what you might think, the full length of the screw is not used. 100% capacity is reached with this portion of the screw being used. Notice that the size of the discharge port also needs to increase, as the amount of refrigerant through it increases. This is easily visible when we remove the slide. Now a brief explanation of the compression itself. The suction gases cool the motor windings and are admitted into the open end of the screw. The groove of the screw will be filled with low-pressure gas. The screw and the gate rotors move, and we see about here that one of the fingers of this upper gate rotor is closing a groove. From here, the groove will be reduced in volume so that the trapped gas is compressed more and more and more. The same action occurs simultaneously in the lower side of the screw at the lower gate rotor. All of this pressure will be discharged through the opening created by the slide valves, allowing the high-pressure discharge gas to exit the compressor section. After compression, the discharge gas, mixed with oil, will flow through this demister and the oil separator. Here this oil mist will be liquefied and thus kept into the sump of the compressor. Without this, the oil would be ejected together with the high-pressure discharge gas. Moreover, the high-pressure gas also pushes on the surface of the oil in the sump, eliminating the need for an oil pump since all lubrication will be done using differential oil pressure. Now that we understand the flow in this compression process, we can examine the details of this new stepless capacity control mechanism. The main parts are the piston and piston valve, the bridge over the two slide valves, and the two springs that push back the assembly to the zero capacity position all the way to the left. Let us first consider the movement of the pilot valve. After that, we will concentrate on how the piston is moved. The pilot valve will move from 0% fully left to the 100% position. In reality, this movement occurs much slower. It can take up to 320 seconds to obtain full capacity from the compressor, that is, using an outlet water control configuration. The movement of the pilot valve actuator rod is controlled in a small box mounted on the outside of the compressor. Two O-rings seal the shaft. The step motor will drive a screw shaft. Connected to this screw is the sector that will twist the pilot valve actuator rod. In line with the actuator rod, a potentiometer for feedback is mounted. By the way, there's a small scale just above the actuator rod. A chassis punch on the rod will enable us to read the compressor's capacity. To finish our description of the pilot valve movement, we can see it here, inserted in the piston. Again, the actual speed is much slower. The purpose of the pilot valve movement is to control the bleed opening in the piston shaft. This bleed opening connects to the low-pressure side of the compressor. Then comes the piston. Remember that this piston movement is linked to the slide valves using this bridge. This piston will be put in motion by a combination of the spring force, high pressure, and so-called dynamic pressure. To explain dynamic pressure, we will draw a parallel with a traditional piston compressor. The suction gas is drawn into the compressor using the inlet valve. The gas is then compressed, but before the discharge valve is opened, the pressure builds up to a slightly higher pressure, the dynamic pressure. This overcompression is about 1.5 to 2 bar higher and will be taken in the compression chamber around the screw just before the slide valve. The piston continues to raise and the high-pressure discharge exits the compressor. Let us consider how this higher pressure is brought into the capacity control cylinder. This picture shows where the pressure pickup occurs in the compression chamber. We also clearly see the housing of the slide vane. Note that the dotted line shows the passage in the cast iron housing. Then there is the flange. Note the tiny hole. Through this hole, pressure and no flow will pass. It is also interesting to compare this tiny hole with the size of the bleed opening we mentioned a while ago. Finally, there is this cover, where the dynamic pressure will be allowed to exert pressure on the left side of the piston. The compressor is started, and because of this, the piston moves to the right, pushed away due to the dynamic pressure. Actually, first, the piston will automatically move to its 12% position, regardless of the pilot valve. This travel is obtained due to the size of the inlet port for the dynamic pressure. Only after 200 seconds, the required startup time, the capacity will be allowed to build up in a sequence of sampling and upload actions. This all the way up to full load operation. Reducing the capacity is somewhat different, since here the opening in the piston shaft will be used to bleed off the dynamic pressure so that the high pressure, to the right of the piston, together with the force exerted by both springs, will become greater than the dynamic pressure and will push back the piston to its 0% position. Note that if an emergency stop is required, the machine will stop immediately. When the machine has a controlled stop, the 12% solenoid valve is activated, and the piston is forced rapidly to the left. This action will quickly balance the pressures so that reverse rotation is reduced and damage avoided. The pilot valve will return to the 0 position, however, it will take its time and follow the capacity decrease sequence. A restart will only be possible when the pilot valve has reached this position, providing no guard timer inhibits this. There is then the stable operating state, the state the machine will operate in most of the time. The balanced forces will allow the bleed opening to remain constant, and only minute compensations will be required by the thermostat, which monitors the feedback from the potentiometer. Capacity is thus steplessly controlled between 30 and 100%. Now we understand the guaranteed optimum operation of another ZH compressor that will be installed in this EWAD 240 or in this 150 kW machine operating on R134A refrigerant.